Alright, so today we will continue the topic of phase transitions. Specifically, we have seen that at a phase transition, or in the separation of two phases, we know that the intensive parameters, variables, are the same. So we have phase A and we have phase B. We know that when those two phases are at equilibrium, so mu A equals to mu B, PA equals to PB, and TA equals to TB. Okay. In general, we also seen that we want to describe the phase transition by using the Gibbs-Duhem equation that was d mu equals minus s dt plus v dp, where here S and V is the entropy per particle and the volume per particle. So, and also we have noted that a phase transition, we can describe it by saying, is there a jump or there is no jump in what? In the derivative of mu with respect to the intensive parameters. So we can say either d mu to dt has a jump or d mu to dp has a jump. So the first order phase transition, when the derivatives are discontinuous, and there is a difference between the entropy of phase A and phase B and the volume of phase A and phase B. Moreover, we can say, well, the derivatives can be continuous, then it's going to be a second order phase transition. So continuous derivative, second order phase transition. And discontinuous derivatives, it is first order phase transition. Now, if we plot a phase diagram of P versus T, okay, white P versus T, so we have three different variables, mu, P, and T, and they're exactly equal at what? At the phase transition. We can have a coexistence line where we have phase A and phase B, and we have derived the Clausius-Clapeyron equation, Clausius-Clapeyron equation for this coexistence line, which is dp to dt equals to delta S divided by delta V. Okay? So apparently this works only for what? For first order phase transitions. This equation is not applicable to second order phase transitions because their delta V can be 0 or delta S can be 0, so there is no separation in terms of Clausius-Clapeyron, but there is a separation in terms of some other equation. Exactly those points, P equals to of A equals to P of B, T of A equals to T of B, and mu of A equals to mu of B. What else can we do, or how we actually use all of this on specific systems or specific models? So the first example is going to be, and very trivial one, is going to be ideal gas. So, is there a phase transition for an ideal gas? Okay, so for us, ideal gas, PV equals N T. Right. So this is okay. It depends on what units, but write it without. So this is the equation of state. It defines different states of the gas. Now I will remind you how we define. So we have a chamber, and inside this chamber we have a lot of different molecules that are wandering around. Those molecules have what? They have some sort of kinetic energy, and they bounce from the walls to other walls, and they do not feel each other. So the ideal gas, the derivation of the ideal gas included an assumption so that the different molecules of the gas do not see each other at all. Okay? So there is no interaction. This is how this equation was derived in the class of thermodynamics. Okay, so for an ideal gas, do we have a phase transition? How we can look on this, how we can understand, is there a phase transition? Maybe there is no phase transition. So the clue is the continuous properties or discontinuous properties of those guys. Now specifically we will focus on first order phase transition. So if we plot P as a function of V, what we will get, right? Very easy. It's always a decaying function. It is nRT divided by V. Nothing really happens to this function. We change the temperature, and maybe something will go up or go down. It will diverge a little bit faster or a little bit slower, but all the different behaviors, isothermal behaviors, indicate what this line represents. I picked a very specific temperature, okay, and for this specific temperature, N was constant, R was constant. I measured the pressure as the function of volume. I change my temperature a little bit, okay, and then I will get another line. I change my temperature even more, and I will get an additional line. Okay. What is common to all of those lines is that dP divided by dV is smaller than 0. Okay. Nothing bad happens in this perspective. This equation is always satisfied. Now you remember where we got this equation from? Stability. So the system is always stable. Okay, we shift something and the system reforms those. There are a little bit more pressure inside the system, a little bit less pressure inside the system. But dP to dV is always smaller than 0. The system is always stable. Okay. Now, those guys, the discontinuous derivatives, they display some sort of an unstable situation. Okay. So for the ideal gas, we see that it's always stable. There is always a negative derivative of dP to dV. There are no jumps whatsoever, right? So there is no phase transitions. Now, we will later learn in this class that phase transitions originate from interactions between the particles inside the system. So a little bit stronger, a little bit weaker interactions. This is what caused, this is the basic cause of large-scale properties that we call phases. They all lie in the specifics of the interactions between the different particles. In ideal gas, there is no interactions between the particles. So we do something to the system, but there are still no interactions, so there is no phase transition. Yes, a question?
Why there is no...
This is how you derive the ideal gas. If you remember, go to the how you derive it.
I know.
There is absolutely no interactions between the different molecules.
Okay.
Physicists can solve two problems. Free particle and a particle connected to a spring. This is a free particle case.
Okay.
Yes.
So,
Alright, wait a second.
how do you prove that the function of continuous or something like that?
What? The second one?
For example,
Is there a jump? Okay, let me ask you, is there some sort of a jump in the volume? This equation describes all the different states. Okay, so for a volume to jump, I should say, well, there is a portion, okay, for some specific temperature when the system can be at volume A and it cannot, at volume B, and it cannot be at volume A plus B divided by 2. This is a forbidden state. Okay? I don't see anything in the behavior of this function nRT divided by V that will say, Stas, this volume is a forbidden state. Do you see something like this over here?
Okay.
I don't. Okay? This is why I say everything is continuous. We'll come to Van der Waals in a second. Yes.
שתי שאלות. אחד, אתה חייב לבדוק את כל הנגזרות, זאת אומרת, נגיד D, mu ל-dn ו-D, dt ל-absolute, כאילו...
So first question, do I have to check all the derivatives? And you have seen that I haven't checked any derivatives whatsoever. I plotted P as a function of V, and I ask, are all the states that are described by this is a model. There is no such a thing as an ideal gas. Everything is almost an ideal gas. But this is my model. And in my model, I ask the following question. Are there jumps? I plot the equation, and I check whether my system is always stable. And for any V and for any P, this condition was satisfied. This means that the system is stable, so it's physical, and then it's fine. This is enough for me.
Okay, ומה עם גרף ל-T, של T למשל, זה רלוונטי?
Alright, great question. What if I could plot not P as a function of V, but P as a function of T? Will I learn something from it? And the answer is, well, you should go and ask what is dP to dt. Are any constraints for dP to dt? We don't know. Right? So what do you have derived? You have derived stability conditions. Stability is intensive, derivative of intensive variable with respect to extensive variable conjugated to it. P and T are not conjugated variables, so I have no idea. Right? So P of T, this is this coexistent line, and I have something about the separation line. This quasi-scope line, but I have no idea what is stable and not stable. I know what is stable only in terms of P and V, mu and N, S and T. Nothing about P and T together. Only conjugated variables are important to determine stability. That's it. This is why I have plotted P and V. Okay? I didn't plot it well because it's nice. No. The only purpose of this plot is to say, look, you have a stability criteria. Look when this criteria is not satisfied. When it's not satisfied, something funky happens to your state, to your system, then you have a suspicion that a phase transition occurs. Okay? Remember, thermodynamics describes monotonic modifications of the matter. You hit a little bit, something small happens. You a little bit more, something else might happen. Phase transitions, it's a huge abrupt change of the whole system. You can even say it's some sort of a non-equilibrium deformation that happens in the system very, very, very fast. Okay, so this is why we are interested in those deformations. This is why we're looking for unstable situations, because they point to this phase transition. Alright, so another name was mentioned, and this is the Van der Waals gas. Now, if you think about physicists in the 19th century, so they developed the ideal gas, great. They developed all this mathematics of thermodynamics, and there are no phase transitions. Now, you do see something happens in reality. You go to the lab and you can transform ice into water, water into vapor, and vapor into ice. Huge, very drastic modifications. So this is not ideal gas. You need something else. You need a simple model to describe phase transitions, which is not ideal gas, but not really far away from ideal gas. The point of physics is not to complicate everything, and then you will scratch your head and say, well, I don't understand what's going on over here because everything is important. The idea of physics is say, we will make some small modifications to a simple situation, and then we'll study those modifications. Will they create something qualitatively different? Okay, so van der Waals gas goes as follows. So first of all, you say the following. So V is the volume of the gas. It can be arbitrarily large and arbitrarily small. Now, van der Waals said, well, if I'm thinking, and then, oh, it's 19th century still. People do not have an idea if the nature is atomistic or not. So his assumption was already some sort of a big step towards atomistic description of the nature. It says the following: the volume is not a real volume. There are minimal volume, which is described by the number of molecules that I have inside the system, multiplied by a constant. And also, so you think about the molecules as small particles, okay? Small balls. You cannot compress the system and create a volume that is smaller than NB. So the volume that you have is actually volume minus NB. This is the true volume of the gas. So in some sense you can say a free volume, because you cannot never compress the system below N, the number of molecules, multiplied by some specific value. Let's call it the radius of those molecules, or whatever. Right? So for us it's clear because we already used to think about system in terms of atoms. Right? So this is the radius of the atom, and this is the number of the atoms, etc., etc. But they had no idea about atoms back then, or at least not the idea that we have right now. Another modification is that, well, the pressure is also modified. There are some sort of interactions. Okay? So the pressure and the particles, they do attract each other a little bit. Remember here, I assume no interactions between the particles. Van der Waals said, well, the pressure is some constant A multiplied by n squared divided by v squared. So the pressure is a little bit higher. Why it's a little bit higher? Because the particles are already attracting each other. Right? So they are pressured somehow. Now, you take those two assumptions and you plug them back into the formula of the ideal gas. So what we're getting that P plus A n squared V squared multiplied by V minus NB equals to nRT. This is the whole story of Van der Waals gas. Yes?
Again, why we are the term in the pressure?
Here, because your pressure is higher than it's, because they are attracting each other a little bit. So the system is already pressured.
It goes like R to the third, so it goes like 1 over R to the 6.
R to the third, R to the 6? What do you mean?
זה הולך כמו 1 חלקי R ב-6.
What is R?
רב מרחק מהזה?
No, I don't. So look, the Van der Waals is a simplistic model. You cannot use something, a very good description of what the molecules are. Okay, so so why that? You will see in a second. He guessed. You will see in a second.
Okay.
Right?
It's connected to the distance between the particles?
What? V? V? No, V is your volume.
Yeah, but is there a connection between...
So this is a concentration, right? A concentration squared. Why squared? Because it's the pressure is somehow defined by the forces between the particles. Yeah. So you basically say, I have a particle over here, I have another particle over there, they are somehow interacted. What the probability is the probability of having one specific particle in one place and another specific particle in another place. That's related to concentration squared because you multiply position of 1 and the position of 2.
Okay.
But I think he guessed. So we can describe it by hand-waving arguments. Why it should be so? I think Van der Waals guessed this. Okay. Why he guessed it? Because he needed something which is still simple enough, still not far from the ideal gas, which works for gases. It actually works. Okay. For dilute gases, the ideal gas equation works. Okay. So he wanted something close, but not, not exactly too close. Okay. So now, if you look on.
It depends on the parameters, not how we can write t by t.
Sorry?
Isn't it dependent on the parameter?
What parameter? So we have two parameters, A and B.
But it's the dependence between them, the relation between them, it changes if there is a phase transition or
No.
No.
Yeah. So the existence of phase transition, as we will see in a second, first of all, A greater than 0, B greater than 0. So for this equation, no matter what A is, no matter what B is, you are going to get always a phase transition. Always. The only thing that will differ is what is your temperature when the phase transition can occur. Okay, so then temperature is high enough. When temperature is high enough, the isothermal behavior, so as P, not T, I'm sorry, this is V. How P is described as a function of V. We will have a smooth decay. Okay, this is for sufficiently large temperature. Now we are going to decrease our temperature a little bit. Okay, so this is for temperature T1. This is for T2, and T2 is smaller than T1. And this goes like this. All right? We lower our temperature even a little bit more, and we are having something that looks like this. Okay? This is T3. And we lower our temperature a little bit more, and lo and behold, that you're getting something that looks like this. Okay. So for low enough temperatures, this equation, for low enough temperature, this equation produces one minima and one maxima. Okay. So this is the one minima and one maxima. You can say, well, Stas, who cares, right? Minima, maxima. We in high school already solved many problems with the one minima and one maxima. Exactly. So this guy is not satisfied. Okay, so there is a region over here. This region. The moment that we have one minima and one maxima, okay, at this region, dP to dV is greater than 0. Okay. What does this mean? That the system is not physical. The system is not stable. It basically means that I have some sort of forbidden region. The region over here. The volume somewhere inside those regions cannot be actual volumes of the system. Okay. Why? Because if the volume is somewhere in this region, the system is not stable and it's extremely fast. We'll go to either volume which is lower or to the volume which is higher. Unstable situation. Okay? It means that small fluctuations drive me away extremely fast to a stable solution. What are the stable solutions? Somewhere here it's a stable solution. Somewhere here it's a stable solution. So Van der Waals gas predicts existence of unstable non-physical situations, and we interpret this as a phase transition. We basically say if we will try to drive the system over here, it won't survive. It really fast will get over here, over there. So if I'm driving my system and I'm decreasing my pressure for a given temperature, at some point I suddenly will see an abrupt change and the volume will jump from this situation to this situation. this value to this value. So if we plot, think about it. Let's plot v as a function of p. It will be a little bit more clear. So if this is v and this is p, so all what I'm saying is that I have something like this. Because a function can never be of this form. This is not a function, right? For any specific p in this region, I have, well, several values of v that can satisfy this function, and it's forbidden. So what I interpret this behavior as a sudden transition. I will get to a specific critical value, VA, and I will jump to some other value, VB. Okay. So this jump in volume, delta V, signifies an existence of a first order phase transition. Yes?
The critical value of the point where the pressure starts increasing with respect to...
Great question. We don't know yet. So you can say, well, this is a critical value, but maybe just before that it's also a critical value. I don't know. I only know that only in this region, dp divided dp to dv is greater than 0. So here it's definitely unstable. But maybe this region spills somehow over towards here and towards there. We still don't know. Okay, we will answer this in a second. Other questions? Yes?
How do you know it will happen in a short interval?
Short interval of time?
Yes.
I know this from my physical experience because I have done experiments.
But what if I'm doing it in a slow pace?
It will still happen extremely fast. You can see this in the lab. So when I was a student in undergrad first year lab, we have something about, I don't remember exactly what the lab was, but there was a very, very, very fast transition. Try to cool down something and you will see that the ice forms extremely fast. Extremely fast. You cannot slow this down. The moment this reaction starts, that the system starts to solidify, for example, or it transforms from gas to liquid, it happens extremely fast. Yes?
Is it enough to equal 0 or does it have to go actually positive? Because it seems like the argument made over there, it seems like it would be enough to just equal 0. It's still not the end.
Please repeat yourself.
If the derivative over there would be equal to 0.
Oh, great. So you're saying that there is a specific place when the derivative is exactly 0. What happens over here? By my argument, the delta V is going to be 0, right? So this is a phase transition or not?
It sounds like it is because it's not a function.
But okay, so great question. So what you are trying to describe is something that looks like this and then looks like this. It's continuous. If it's continuous, it's a second order phase transition. So there is going to be one specific temperature. Okay? So please understand that. This happens for different temperatures. For a given temperature, which is low enough, I can observe a phase transition as a function of P or V. But there is a very specific temperature, T equals to Tc, a Curie temperature or critical temperature, for which dP, there is no maxima or minima. Those two maxima and minima, one minima and one maxima, it coincides in one specific point. Okay, so I have a critical point, but the second derivative is also 0. So the first derivative is 0 and the second derivative is 0. Okay, so there is no jump in the volume. There's something else has happened, and this is a point of a second order phase transition. Okay. When there is a jump, first order phase transition. When there is no jump, okay, but there is dP to dV equals to 0 and the second derivative equals to 0, this is a critical point of a second order phase transition. Yes?
אתה כאילו נגיד, יש לך טמפרטורה קבועה, אתה משנה את הנפח עד נקודה מסוימת, ואז מה קורה? זאת אומרת, האזור הבעייתי זה בעצם אזור שבו המערכת לא יציבה, אבל איך זה מתבטא במציאות? כי כאילו אני לא רואה כאן קפיצה.
So okay, so the question is, I don't see here a jump, how I can see a jump? So you take a system, let's assume this guy. Let's erase the black line. And you start from a high volume, you have a gas. And then you start to increase the pressure. You pressurize your chamber more and more and more and more. So you pressure a little bit more, the gas is compresses a little bit more. You pressure a little more, the gas compresses a little more. And then you do something like up, it jumps in 1 second. So you press a little bit more, and the whole volume is just decreased by a lot, not by a small amount. So beforehand you have an infinitesimal modification of the pressure. You get an infinitesimal modification of the volume. But at some point, you do a little bit more pressure, and the whole system just jumps like that. And you can see this in an experiment. Yes. Yes, yes. Well, whatever I have done for this plot, I just reversed the axis. It's the same plot. Take this, rotate it by 90 degrees, and reverse, and we'll get the same plot. Okay. Now, this is actually used. Have you ever seen robots that can grab stuff? So it's actually a complicated engineering problem. How you can devise something, a hand, that actually can grab a cup without breaking it. So if you look on the experiments on robots, they crush all the stuff all the way around. Why? Because you continuously express too much pressure. So one of the ideas how to solve it, they use some sort of a sandbag. Okay, so the sand, well, you can describe sand as some sort of a bag. So the sand is actually covers the object. Then you extract a little bit more pressure. The volume of the sand decreases dramatically, not by a little bit, but by a lot. And then it grabs the object, and then you can move it from one place to another. This is based on this property of phase transition. The sand as a gas can also have some sort of a transition. It's not a gas liquid, but it's some sort of a phase transition. Okay, so there was a question of how do I know what is the critical pressure and what is the critical volume? Maybe I should bring the movie of those robots grabbing stuff. It's actually,
the derivative is zero.
oh, so your suggestion is that, well, let's find this point of minima, this point of maxima, all right? And we will say that this is a critical transition, right?
Maybe the second derivative.
Okay, okay. Now, what is wrong with your suggestion? The suggestion is wrong.
Second derivative.
No, you're not trying to use physics. This is what's wrong about your suggestion. What we know that happens at phase transition. So we have this, right? So your suggestion, let's take this. This is PCA, the critical pressure at phase A. Let's take this, which is PCB, right? The critical pressure at B. So we have, this is phase A, this is phase B, from this point onwards. Phase B, from this point inwards, phase A.
I think it's depend if the function is convex.
Wait. I told you haven't using physics, you're trying to use mathematics. The physics is that the pressures are exactly the same. The pressures at phase transition between phase A and phase B have to be exactly the same. So if I'm choosing one at maxima and one at minima, they're definitely different, so this is not the critical point. Okay? Physics here, not mathematics about, so we are now, yeah, we use some sort of properties of the functions, but physics tells us that at phase transition, PA equals to PB, mu A equals to mu B, and TA equals to TB. You have to use this. Okay? So we need to find some other point. We cannot choose this point in the middle because we already know that this is not satisfied over here. This is not stable, and some point in the middle. So this is why I told you that the unstable region spills over. Okay, so somewhere over here, we will have to find a point when this is VA and this is PA. And this is exactly the same pressure at VB. PB equals to PVA, but the volumes are different. Okay. Pressure stays the same. It's the intensity parameter, and it has to be the same for both phases. Now there is a technique how to find it, and it's called Maxwell construction. Maxwell, the same guy from Maxwell equations. Maxwell construction. Yes.
לגבי השינוי הקטן, כאילו כל הדיבור על האי-יציבות זה ששינוי קטן באחד מהפרמטרים יגרום לשינוי גדול בפרמטר האחר.
Yes.
אני מבין את הרעיון הפיזיקלי, פשוט בגרף, נניח לבחר נקודה שהיא באזור הזה, אני משנה קצת את הנפח או את הלחץ.
Okay, so there is a still general disbelief that a small change in one parameter can lead to a large change in another. If I have this function and it's a discontinuous function, it's decaying and then it's decaying again. So here is delta P, and I can make it arbitrarily small. Here is delta V, and I cannot make it arbitrarily small. That's the whole answer. There are functions that are discontinuous, okay, in the value of the functions as a function of the parameter. No, if there is a jump. It cannot be like that. Do you know? Do you familiar with any mathematician that can define a function like this? There is not a function, right? Because I know from my physical experience that there is a jump in the volume. Look, I know what the result is because I have seen it with my own eyes. Supposedly, I've never been to the lab. Supposedly. Supposedly. Okay? Supposedly, I've seen a transition. Now I'm trying to use functions and mathematical representation to describe this. Now, van der Waals provided a model. Okay, so the model is P plus A n squared divided by V squared, V minus N B equals to N RT. He says this model described gases and liquids and transitions. And I went to my experimental lab and I checked this and it works. And it works. And now I try to understand what actually this equation describes in terms of phase transitions. So it is working very, very, very well to describe gases and transition to liquids, right? And now I'm trying to understand what it means mathematically. And mathematically, when I plot this function, C as a function of V, I have something like this. I invert it, and I have this. This is impossible for a function, right? So I need to describe this transition somehow. The way I choose to describe it because basically what it says that this is this region. The model fails over there. The model is not true. Something else happens. And my choice to connect points by straight line is just basically saying I have no idea what's happening in between. Okay? I have no idea. Something happens. Okay? The volume grows, and if you look on this with your HD camera and you will film the movie or all the different molecules in extremely high resolution with extremely high speed, you will see that everything is continuous. Everything is continuous, but it's not in equilibrium. Okay? So there is some sort of a transition that appears that cannot be described by thermodynamics. And how I solve it? I just say this is an unstable and unphysical situation, meaning thermodynamics, equilibrium thermodynamics does not describe these regions. For me, I approach over here, there is a very fast transition to here. Of course, there are in between volumes, right? The system does something. The particles and the volume is not coming from thin air. The system does something, but I cannot describe it by infinitesimal change of this equation. Okay. So this is a non-equilibrium, an equilibrium that live together.
You cannot say what in this region? Nothing?
I have no idea. Well, if I'm a physicist from the 19th century and all I know is thermodynamics, I cannot tell you whatever is happening inside. Now I can tell you, yes, there are atoms and the interaction is growing and the atoms are actually trying to be more together or more apart, and they do it collectively on a very large scale. I can film it and I can see what is actually happening. But thermodynamics does not describe this. It describes the endpoints, the equilibrium states. In between there is no equilibrium state. That's what it means. This phase, this jump basically says, over here there is no equilibrium state with VA plus VB divided by 2.
Yeah.
Nothing. Alright, so how we find this critical point? You ask a lot of questions. Let's try and find the solution. So I'm going to use this idea of dP to dV smaller than 0, okay, the stability criteria, and the description that I'm using, but not in terms of P and V. I want to use free energy. F equals E minus Ts. So basically, if I will plot F as a function of V, what I claim is that I will get something like this. And in a second you will see why. Okay? The unstable behavior over here is basically saying that I have a jump between some VA to some VB. Okay? In between, there is an unstable situation that I do not know what happens over there, so I will try to build something which is called the Maxwell construction. He says, let's throw out of the window the description by van der Waals and put here some sort of a straight line. Okay. How exactly we do this? So, as I mentioned, exactly at the critical point, okay, where the two phases coexist, and this is what I know, that two systems can coexist at phase transition. Okay? So I know at coexistence, mu A equals to mu B, and PA equals to PB, and TA equals to TB. Now this is trivial because I'm using the same temperature, so I'm only looking on mu A equals to mu B and PA equals to PB. What is dF? dF equals to minus S dt minus P dV plus mu dN. Now, temperature is not changing, the number of molecules is not changing. So I have that dF dF plus P dV equals 0. At critical point. At critical point, okay, I can say the change in P is 0, P is constant. So at critical point, dF plus P, PV, right? Phase 1, phase A, equals to F plus PV at phase 2.
Isn't it just Gibbs?
What? This is a free energy.
F plus PV.
F plus PV?
Oh,
No. We started with this guy. We started with this guy, and the differential of the free energy, it is what it is.
No. F minus PV gives energy. Gives PV.
Yeah. Well, because you haven't subtracted anything else. Yes.
Why is the change in pressure?
At critical point, the pressure is exactly the same. Okay? You will see in a second. Just a second. Patience. A little bit of a patience. Okay. So what I'm saying is f of a plus p v of a equals f of b plus p v of b. F of a minus f of b equals to minus v of a minus v of b multiplied by p. F of a minus f of b divided by v of a minus v of b equals to minus p. Okay. So this equation is enough because what I'm saying is the following. If I have f and I have b, in order to find the critical point, so at some point there is something funky going on. This equation says, okay, so you find a specific critical f of a, you find a specific or critical f of b, okay. F of a corresponds to volume v of a. F of b corresponds to the critical volume v of b. How you find those critical points? Well, you plot a tangent to this point, which is df to dv. It is minus p. You plot the tangents to this point, which is df to dv equals minus p. When those two tangents are exactly the same, you can put one straight line between the points. The slope of this straight line is the pressure at VB and is the pressure of VA. Okay? By doing this construction, you found when you can actually connect specific points at phase A and specific points at phase B, you found your different distance between VA and VB. Okay? The pressure stays the same, the volume is performing a jump. And if you can't find this transition, Maxwell's tells us forget about whatever happens in between. So you basically replace whatever function that you have in between V and VB by a straight line, because in any case you cannot describe what is going on there with the use of thermodynamics. And you say here it's an unstable situation, and I simply replace it by a straight line, and the slope of this straight line is the pressure at phase A and phase B. And the way that I build this straight line actually helps me to find what is the critical VA and what is the critical VB.
We can do an analogous process with enthalpy and temperature, right?
Yes, yes. You can also do something very, very similar on the PV diagram. It's actually more convenient, and this is how it was originally done. So for P and V,
can I ask something?
so in P and V we know that we have such a situation. And as we know, we cannot say this is the critical volume and this is another critical volume, because it doesn't work, because the pressure of this volume and the pressure of that volume is not exactly the same. Okay? So here we connected the 2 points by some straight line. So Maxwell construction on the FV level is translated through Maxwell construction on the PV level by saying, since my pressure is exactly the same at phase A and phase B, I will find some PC, this is my critical pressure, and it will define me VA, and it will define me VB. Okay. And instead of going down and going up and going down behavior of the van der Waals equation, I'm simply saying I have a straight line over here. Is this the true behavior of the system? No, it's not. It's not. It's just a way by how Maxwell tried to describe whatever is going on here. So the description of Maxwell is as follows. You can follow this line up to some critical point. At this critical point, you jump extremely fast over here, and then if you increase your volume a little bit more, you will continue your journey back on this black line. All right? So this is the Maxwell construction. And how you find the critical pressure, and how you find V and VD. So we have already seen that you need to find a derivative of F with respect to V at different points, and you should look for 2 points with exactly the same slope. What it means on this diagram over here. So look on this guy. Okay. So we have FA minus FB equals minus VA minus VB multiplied by P. Okay. So this is VA minus VB. Yes, yes, what? So this is the area. This is the area. Whatever is written over here, this guy, this is area. Why? VB is larger than VA with minus over here, so that's a plus, multiplied by P. So whatever written on the right hand side of this equation is the area under this straight line. Okay. So this is this area. This is the right hand side. What is the left hand side? What is the left hand side? Look on this equation. dF equals to minus P dV. So if you take an integral, okay, so this is what?
Linear under P.
FB minus of FA minus FB. Right? Well, it depends on what is the minus over here. Okay? So FB minus FA, right? But because of the minus, we're going to have FA minus FB. So this integral, the left hand side. So the right hand side is the area under this straight line. The left hand side is the area under the actual function. Okay. So when the area under the actual function equals to the area under some straight line, this is what we call Maxwell construction, and this defines the volume, critical volume of phase A and the critical volume of phase B. Okay. This is how you will see an exercise during your with your TAs. This is how you find the critical volumes. Okay. You basically compare the areas under the actual form of the function to the area of some construction when you say, I don't care about this slope over here. I will put a straight line, okay, and compare the areas. Where it's coming from? It's coming from all this description and the fact that pressure at phase A equals to the pressure at phase B. This is a physical assumption, physical correction. Yes.
We proved that D of F plus PB is equal between the two phases.
Yes.
So we can say that F plus PB difference between the two phases is constant. How can you say that? At
the critical point. So this guy over here, this guy, it's exactly at the phase. It's exactly at the phase between those two, at the phase transition. Not general, because we used, remember, this was the question, P is not constant. I assume that P is constant, and then I can transform this equation into that equation. Okay? But it only for constant P, and it only means that at the point of phase transition, okay, P is constant between the two phases. Okay? Yes?
Can there be more than one
Phase transition? So yeah, bring me a more complicated function, and there could be 2 phases, 3 phases, 4 phases. So for example, if you, those particles are single atoms, and if you have, for example, molecules that are connected by, so the molecule is actually 2 atoms. So some configurations of the inter-atom positions can bring you additional phase. So it depends on the amount of degree of freedom. Here it's a very small amount of degrees of freedom. You increase the amount of your degrees of freedom, you can obtain general phases. Yes?
Just to make sure I understand, when you said that df equals minus dt, dt equals 0 because of stability, and the reason df...
No, dt equals 0 because I'm looking on a specific line with constant temperature.
No, not stability, sure. Because
I use a constant temperature, and I do not let any additional particles inside the system.
So you're assuming that the number of particles stays the same?
And the temperature. All those lines that I plotted are always for a very specific temperature.
Because the phases are in equilibrium.
Yes.
FB minus FA is not the area under.
It is. I would, because of all the minuses here it is. Okay.
It's FA minus FB.
But you have a minus over there.
Yeah, but
the minuses get it. Okay.
But get it inside. You get VB minus VA.
I will explain it to you later. Okay. It works. Believe me, it works. So all the minuses are exactly the right place. All right. What you will see. I have to move on. I'm sorry. I have to move on. Okay. So you can use this technique for any given temperature. And you can find the critical VA and VB. So I will have, for example, one specific temperature, and I will point out that there is VA and there is an additional VB. Okay. I can modify my temperature a little bit, and then I will find that I have another VA and another VB. Okay. And I can modify my temperature a little bit more, and I will have another VA and another VB. So you will see in an exercise provided by OTA. So if this is your temperature and this is your V, you can get a phase diagram. So this is phase A, this is phase B, and there is a separation line between those two. Okay. So this is not P over T, okay, as we've seen in Clausius-Clapeyron. It's something different, and we can plot this and find this by solving for each temperature and finding the critical volumes. Okay, and we see that this is phase A, so there is a volumes and the temperatures where there is something that we call phase A. There are volumes and temperatures where there is something that we call phase B. In between, we have unstable regions. Those are volumes that cannot be described by equilibrium thermodynamics. The system will never be over there. What I mean by never be, yeah, we can push it towards some specific volume, but it will really, really fast escape this region because it's not stable, right? It's like putting a pendulum on top in the highest position. Immediately it will go down, right? So this is what happens over here. So there are stable phase A, there is stable phase B, there is a phase order, first order phase transitions between those two, and there is a very interesting point over here. You see, at this point, there is no jump between VA and VB, exactly at the top. VA equals to VB. Here, a second order phase transition occurs, and this is the critical temperature. Okay. For any temperatures that are below TC, first order phase transition can occur. For any temperatures that are above TC, no phase transition can occur. Exactly at TC, a second order phase transition occurs. There is no jump. Okay? The volume of the system stays the same. The entropy is basically continuous, but there is a phase transition. So you can actually see a transition from liquid phase to gaseous state. We will talk much more about, hopefully, about second order phase transitions when we'll talk about Ising models by the last third of this class. This is it for thermodynamics. Okay. Any questions about thermodynamics? Yes. I don't understand the thermodynamics. Nobody really understands thermodynamics, but it's an important subject. Yes. Okay. An additional explanation. What is this Bell function over here? So it is not a Gaussian, and it's probably not a parabola. What this function is? So I can, by the power of Maxwell construction, for any given temperature, find VA and VB, the critical volumes at phase transition. So what I'm going to do that at each temperature, you will do it on your own with your TAs. So for any temperature, I'm plotting these two volumes, and I do it for different temperatures. Okay, so as I will raise my temperature, those volumes will start to getting closer and closer and closer and closer until at some critical point, they will coincide. Okay? So while there is a finite difference between the volumes, this is a first order phase transition. When there is no difference between the volumes at the top, this is a second order phase transition. Okay? That's what all it means. So what you will see that exactly at this point, if you plot P as a function of V, this is what you will obtain. So there is no maxima and no minima. The first order derivatives is 0, and the second order derivatives is also 0. Yes.
שאלה כאילו קצת עוד שורה על החומר, אבל עוד כזה שבועיים וחצי יש לנו בוחן.
Yes.
והבוחן יעסוק בעיקר בתרמודינמיקה.
Okay, so a question about the quiz I will answer by the end of the class this class today. Okay. Any other questions?
I have a question.
Yes.
In the graph of van der Waals class, we see the upper region when the fraction has no maximum and minimum.
Yeah, it's monotonically decaying.
Yeah, and then it goes more and more.
And then a critical point develops. Yes.
Okay.
So this is over here. This is over there,
Yeah.
and exactly this boundary is when there is no jump in the volume, and this is the second order phase transition. Okay, so we're now starting a new material which is called statistical mechanics. Different approach, different ideas. So the point of view of thermodynamics is the matter is continuum. There are some equations of state that describe the system. There is a small number of parameters that define equilibrium states, and by writing those equations of state, we can actually understand matter, right? But as we've seen, there are things that we cannot fully understand, and in a lot of cases we want a more specific equation. So thermodynamics is very general, but because of this generality and high applicability, it's not specific enough. We need to understand a little bit more about what exactly happens around us. What happens to different materials, what happens in different systems, how we can reach equilibrium, how we describe equilibrium a little bit better. Okay? So this is the point of view of statistical mechanics. Statistical mechanics tries to model not from a top-bottom approach, but it says, well, I look on the different models, and I will try to define or to use simple microscopical descriptions in order to understand what is going on. So thermodynamics, it's very general, very top-bottom approach. I don't really care about what's going on inside. I have this thermodynamical laws. There's a first law of energy conservation, and I have some general properties of entropy, and that's enough. Statistical mechanics starts from, well, no, I need some description, microscopical description. It should be very general, but it should start from some microscopical interactions, and I will build up all my understanding about physical and stochastic systems that are around me, starting from those microscopical descriptions. Now, of course, we cannot include everything inside our model, okay? But the idea of physics, if we include just the essential parts, it's enough to understand the general properties. Now, the idea, we can start describing that, well, we know from quantum mechanics that we have states. So I can write down d to dt, the Schrödinger equation, right? Okay. And this Schrödinger equation already tells us, well, there are states inside the system. The states can be continuous, the states can be discrete, but there are states of the system, and there is some development of the state of the system as a function of time. Okay? Of course, you can say, well, how I find those states? Well, I have to solve the stationary Schrödinger equation. And this guy defines the states that we have. Okay? So we have a definition of states from the quantum mechanical perspective, and how the system state changes as a function of time. This is the time-dependent Schrödinger equation. Right? But what if I have, for example, not quantum mechanics, but I'm still living in the world of before quantum mechanics, and I have this equation of Newton, F equals to ma. Okay? So what happens over here? Now, even for this, I can say, well, in general, I can also think about a system in a quantum mechanical way as, yeah, there are states. Okay. So I will plot P, it's not pressure, but momentum, and I plot R, okay, and I will plot the streamlines of the system. So for example, if I have a pendulum, the streamlines on the system look like this. Closed line. Okay, and the system flows like this. And if my momentum is too high, it's going to be something like this. So those are the different flows that I have inside the system. I can take this phase space, and this is a phase space when I have a momentum and I have a coordinate, and I can divide this phase space into small quadrangles. All right, and then I can say, well, this is the state of the system, right? So in quantum mechanics, there is a natural description of states by the means of Schrödinger equation. In classical physics, when there are no states, everything is continuum, I can divide my phase space, okay, two states, and I can say, well, this is a state, and this is a state, and this is a state, and this is another state. The whole idea of statistical mechanics is that the system is running over different states as a function of time. Okay, so we can think of our system as composed of different states, and it can be specific states defined by the position and the momenta. Those can be the states defined by the energy. Those can be some configurational states, but they're always a way to describe a state of the system. And as a function of time, those states can be different, they can be small, they can be large. I don't really know. But what I do know, that there is a way to describe the system as going from one state to another as a function of time. So this is the time trajectory. As a function of time, the system jumps from one state to another, then to another, and etc., etc., etc. So this is my microscopical description. I'm thinking of the world, the matter of the system as a composition of states that this system can occupy as a function of time. And when I watch the system, it's continuously jumping from one state to another as a function of time. So, for example, if I will measure magnetization of a chunk of a metal, so this is time, this is m, and the magnetization will do something like this. Okay, so this is my magnetization as a function of time. I can basically say, well, how I describe the different states of the system. I can just plot parallel lines and discretize the vertical axis of n. So I will have a jump from this state to that state, to this state, to this state, and etc., etc., etc. Okay, so here I have 1, 2, minus 1, minus 2, plus 2. So this process,
continuous jumping.
Alright, when I'm measuring the system, I'm not looking on it continuously, right? I'm taking photographs. The system does something, you can say the system does something continuous, so those positions are continuous. But when I'm measuring it as a function of time, I take a picture, I wait, and then I take another picture.
Yeah.
I always do it like that.
If you will take it quick enough.
Even if I'll take it quick enough, I will always have a finite rate. And there is a limit to my rate. And there is a limit to my memory. Yes. But it's really, so you can say, well, Stas, there are more states. It is fine. I will define the states of the system. I'm using, for example, my equipment to define the states of the system. It's also possible. And I'm looking on the system as it transits from one state to another as a function of time. Now, we need to make some sort of a connection from this behavior. So here, again, I'm trying to connect it to thermodynamics. Thermodynamics, very small amount of parameters. Energy, pressure, chemical potential, volume. Here, states that are actually depend on, I don't know, all the different positions inside. It can depend on whatever I want. I need to connect quantities that I can measure or think about them in statistical physics, and the same quantities that are already familiar with from thermodynamics. For example, one quantity is the energy. Okay. Now, what is the energy in thermodynamics? If I have many particles, is there a constant energy? So the energy that we actually use in thermodynamics, it's an average quantity. Okay?
Right.
It's an average quantity. So if I'm looking on this system from the thermodynamical perspective, okay, from the thermodynamical perspective, how I'm going to define the energy? I'm going to define the average state of the system. So for example, this guy over here is going to describe the average magnetization. I can measure the energetic fluctuations of the system, and I can obtain the average energy of the system. The energy that we are used to in thermodynamics is the average energy of the system. So what is my average energy? If I'm looking on the fluctuations, on those small jumps of the energy as a function of time, it is 1 over n, the number of observations that I have performed, a sum of all the different measurements that I have seen. So EI is the ith observation of the energy. This is the first, this is the second, this is the third, this is the fourth, etc., etc. At each point of time that I measure the energy, and the average of the energy is the total sum of all the energies that I have measured divided by the total number of measurements. Okay. This is called temporal averaging. So if I'm going to a lab, what I'm going to measure in my lab, I'm going to measure a temporal average. I'm going to track the system, I'm going to track its energy, for example, or magnetizations, or whatever the quantity that I can measure, as a function of time. I will measure it at specific times. I will sum up all my measurements divided by the total number of measurements, and this is the average energy that I had. Now, so when I'm thinking about statistical mechanics, and if I want to connect it to thermodynamics, I need maybe dynamics, right? Because how I measure quantities, I follow the system. The system is a dynamical system. It modifies its values as a function of time. So maybe I need to describe everything in terms of equations of motions, right? I need the time-dependent Schrödinger equation. I need what? I need the Newton equation. I need to follow the system as a function of time in order to derive those variables. This is bad. Why it's bad? I don't want to follow the system. I believe that in equilibrium, I don't care about the dynamics of the system whatsoever. Right? So I somehow need to reconcile this assumption, or this, well, it's a truth, empirical truth, that the energy that I measure, it's a temporal averaging, and I need to follow the energy or the system as a function of time. And I don't want to do this. And statistical physics and thermodynamics tell me you don't need to follow the system as a function of time. You need to let it equilibrate, and then it doesn't care about the time. It doesn't care about the dynamics. It cares about something else, equilibrium properties. Okay, so what do I do? Let's say the following thing. So we have this E average, which is 1 over n, a sum of from I to n, EI. I will call by E nu the possible states of the system. Okay, so EI is the energy at measurement point I. E nu is the energy at state nu. Okay. So I want to write this E average as what? As a sum over, let's call it nu goes from 1 to infinity. Let's assume that I have infinite number of states inside my system. I here have 1 over n. Here I have the total number of visitations in state nu multiplied by E nu. So I have a sum, and instead of counting E1, E2, E3, E4, I'm looking E1 is the energy at state 0. Great. That's E5 is also an energy in state 0. So let's combine them all together and count not as a function of the measurement time, but count as a function of the states in my system. Right? So I basically reshifted the sum that I have over here. And this exactly equals to that. Okay.
What is n?
N is the total number of measurement points. It's the same n over here.
Okay.
You can think about it as a function of time.
Why we are going to infinity?
How many numbers of states do I have?
So the total number would be, some of them will be at 0.
Maybe some of them will be 0.
For sure.
Maybe some, yes.
You
Yes,
can
for sure.
measure n times and having...
Well, not 0, but very close to 0. Okay,
How can you measure n things and then have infinitely different...
I'm a theoretician and I'm very strong in theoretician. I can measure. Look on this. This is simply a resample of the sum over here. Okay? So I'm basically saying I have E0, E1, I'm starting from 1. E1, E2, E3. This is E0, and this is E5, and this is E0. So this sum, which is E1 plus E2 plus E3, equals to 2E0. I have been at 0 state 2 times, 2E0, plus 1E5. I'm not doing anything suspicious. I'm just saying, well, I have different boxes now. Beforehand, I had the boxes which are the number of my measurement. Now I have boxes which are the state position of inside my system.
What? You mean the probability weight?
The number of visitations in state nu.
Divided by n is the probability weight.
Oh, so what is this guy? What is this guy? 1 over n, number of visitations in state nu. Who have been to my probability class? Yes, so what is this? Probability, not density, just the probability. This is the probability according to the law of large numbers. Law of large numbers.
You're assuming that they're identical.
Oh, I'm assuming something that is called an ergodic hypothesis. I will describe to you in a second. Law of large numbers, so I'm assuming the n is large. N is large, and this guy, I will say this is P of nu. What is P of nu? The probability of the system to be in state nu. Probability of a system to be at state nu. Okay, so what I have got E equals to sum over n from 1 to, I from 1 to n, EI equals to a sum over from nu 1 to infinity, P nu, E nu. This is by definition what it is. In Hebrew it's called tohelet. Tohelet, a mean, okay, so it is an ensemble mean. Ensemble mean. I don't care about the dynamics when I calculate this quantity. I only need some stationary distribution, stationary probabilities of the system to be in this state and of the system to be in that state. All the different states P nu, I have some probabilities. Okay? And in statistical physics, at least the kind that we will study in this class, we have E temporal average equals to E ensemble average, and this is called an ergodic hypothesis. Why it's a hypothesis? Because maybe the law of large numbers does not work for our system. And our system, n is not large. The way I stuck in some place for too long. There is a bunch of different conditions where the law of large numbers won't work. So this is a hypothesis. And I'm assuming when I'm studying physics, statistical physics, for undergraduate studies, that the ergodic hypothesis work and I can forget about tracking the system dynamically, and I only need some information about those P of nu in order to describe average values. Average values are also described by thermodynamics, so this is my connection between the statistical mechanics to thermodynamics. I need somehow to define those P of mu's, and the moment I can define them, and though my models in statistical mechanics should define them, the moment I know how to define them, I can calculate average values. I can calculate average values. I know the laws of thermodynamics. And this is the connection. And statistical mechanics is how I define those P of mu. Yes?
What if the energy state is distributed like the shear?
So there are different systems when the ergodic hypothesis does not work. My PhD thesis was named the broken ergodic hypothesis in complex systems. So there are plenty of systems when this is not working, but it's not for this class.
The shear distribution is one of them?
No, yeah, for this distribution won't. Okay, so we are done for today. What we are going to study is how to define those P of mu's. Okay, for different models we will have different ensembles, and we'll find that there are not a lot of ways actually that you can use in order to define those P of mu's. In equilibrium, there are 3, 4, 5 different ways that you can use in order to define those P of mu, and this is why everything is universal. But I will see you on Tuesday. We will continue from here. Bohan. So the quiz is 2 weeks from now? Okay, so the quiz is 2 weeks from now, and it will include whatever we will finish by next week, next Sunday.